Okay, good day. This is AP Calculus. I am Mr. McColley. This is the presentation for section 6.5. Now let's get right to it. Today we are going to be talking about the 6 inverse trigonometric functions, and we're going to differentiate them, and then we're going to apply that at least in the example that I have, we're going to do a related rate problem. And so we're reviewing related rates, and then finally we're going to talk about the basic differentiation rules for elementary functions. And there is one page in this particular section that you're definitely going to want to bookmark, because when we start reviewing for the AP Calc test, we're going to kind of keep our eye on this page, because this basically has the entire table of all of the rules that you need to know, at least for differentiation. So let's get to it. And I want you to remember, especially for the AP Calculus exam, is that these things are equivalent. Arcsine and sine inverse is what we usually called it in class. And so this is what would be on your calculator, and this is, excuse me, this is the way that you might see it on the AP Calc test. In fact, I've heard previous students tell me that they see both of these two things being written. But let's kind of review what that means. So if we're talking about just arcsine, so let's just talk about arcsine for a second, and then you guys can apply the rest of it, apply the same type of concepts to the rest of them. So when I say, what is the arcsine of this variable here, the arcsine of this variable here? And basically, I know I have theta here, and I think that's kind of a misnomer. But what this thing really does is it says, okay, if the ratio of, because remember sine is opposite over hypotenuse, so if I say x here and h here, what the arcsine does is it says if I have the ratio arcsine of whatever x to h is, that is going to return an angle measure. So this is the ratio of sides, and in this case it's the opposite over the hypotenuse. And when you take the arcsine of the ratio of whatever x to h is, it's going to return that angle measure. And that's what's going to happen here. So just quickly revisiting that. Again, it's the same for arc cosine. If I had the ratio of, we'll call this A, if I have the ratio of the adjacent side to the hypotenuse, I will get the angle using arc cosine. And if I have the ratio of the opposite to the adjacent side, it will also return that angle measure. So the inverse trig functions find angle measures, the regular trig functions find ratios of sides. Now, the differentiation rules for trig functions are given here, and they are, as you can see, fairly complex, and they only give you the chain rule versions of all of those. So this is the arcsine of some expression in terms of x, and this u prime here, it's going to refer to the derivative of whatever is inside that composed function with the arcsine function. All right. And then the last thing I want to talk about, because we'll go back and forth to this this table that I've created here. And so the last thing I want to talk about is, when you're looking at this, check your book out. Excuse me. And on page 378, there is this basic rules of elementary functions. It's in a little kind of almost khaki looking box. And there's 24 rules there. And that's essentially all the rules that you need to know. So when we start reviewing for the AP Calc test, we're going to use this page quite a bit. All right, so jumping right into some sample problems. I'm looking on page 279, number 28, and it says, in number 28, it says this. It says, given the secant of the arctangent of 4x. And then it wants us to write this thing in algebraic form. So I'm trying to write in algebraic form. So let's break this down. And it goes back to what we had talked about a little bit earlier. What does this thing do? It says, well, take the ratio of the opposite side to the adjacent side, and it will give you some angle measure. So essentially what it's saying is that this 4x is the ratio of the opposite side to the adjacent side. So if I want to write 4x as a ratio, I'm going to write it as 4x over 1. And so what that tells me is that this thing right here is going to be 4x, and this side right here is going to be 1. All right, now, is it exactly 4x and exactly 1? I don't know, but I know that that is the ratio of those two sides. And that's all that really matters, because we're going to have similar triangles regardless of how long these sides are. So what that does is this arctangent is going to give me this angle measure theta. So I get the secant of theta, and I remember that the secant of theta is 1 over cosine of theta, which is essentially the hypotenuse over the adjacent side. Now, the problem here is I don't know what the hypotenuse is yet. I don't know what that is. But I do know two sides of a right triangle, so I can use Pythagorean theorem. I can say that 1 squared plus 4x quantity squared is equal to the hypotenuse squared. So I get 1 plus 16x squared is equal to h squared, and then I can say that just h is equal to the square root of 1 plus 16x squared. And so that is my hypotenuse. So now I can take the adjacent side, which I know to be 1, and the hypotenuse, which I know to be the square root of 1 plus 16x squared, and I can just plug them in. So the secant of this is going to equal just, well, because it's going to be over 1, it's just going to be equal to the square root of 1 plus 16x squared. And that is going to be my algebraic form of the secant of the arctangent of 4x. Okay, moving on. Now we're going to start talking about some derivative rules, and I thought I'd start with an easy one and then do a hard one. So an easy one, they start, number 44 is just f of x is equal to the arcsine of t squared. So again, we have a composition of functions. We've got the t squared function, we've got the arcsine function. So we are going to have to complete a chain, and from this table of rules, the arcsine of u is equal to the derivative of whatever u is divided by the square root of 1 minus u squared. So that's pretty easy. So if I say that the arcsine of u is equal to u prime over the square root of 1 minus u squared, I can say, all right, well, my u is equal to t squared, and then du equals, or du over dt, excuse me, I was doing my integral notation there, but du over dt is going to be 2t. And just to fill in that, because this is what I'm normally used to, and I'm using a different notation, this is the same as u prime. So f prime of x is just going to equal, I'm going to use this expression, so I'm going to put my 2t on the top, and then I'm going to go the square root of 1 minus, and then u squared is just going to be t squared squared, so t to the 4th. And again, if you saw what we did in this first problem, you'll see how they came about with these equations. They're very similar. All right, let's do one that's a little bit more challenging. I got another, oh, I added that page, sorry. Number 58 on the next page basically says this. It says, find the integral, or the derivative, of y equals x. Let's see here, it's arctangent 2x. And then it is minus 1/4 ln of the quantity 1 plus 4x squared. All right, so we have a lot going on in this one. And individually, none of these things are overly challenging, but we need to look at them separately. So in this particular problem, I have a product. I have this x here, and then I have an arctan of the 2x, and this thing is a chain inside the arctan. And then I have this ln, and it is chained with this expression. So I have a product, a chain, and another chain. Okay, well, might as well get to it. So dy over dx, or y prime, whatever one you like to use, is going to be the first, so x, times the derivative of this expression. So remember, arctangent is going to be the derivative of what's inside over 1 plus the whatever's inside squared. All right, so we have the derivative of 2x is just 2 over 1 plus whatever was inside 2x squared. So 2x squared is 4x squared. I suppose I should take a step back and say the quantity 2x squared is 4x squared, plus the derivative of the first, which would have just been 1, times the second, which would have been the arctangent of 2x. Okay, now this one, since I have a constant out front, I'm just going to leave my 1/4. Now the ln rules. Remember, the derivative with respect to x of ln of u is equal to 1 over u times u prime, or du over dx, whichever one you like. So I'm going to rewrite this as 1 over what's inside, 1 plus 4x squared, times the derivative of that expression. And the derivative of 4x squared is 8x. All right, so not a whole lot I can do to simplify this because I have 1, 2, 3 terms. So we'll do our best, and we'll finish it off by bringing the 2 to the top. So I got 2x over 1 plus 4x squared. This fraction cannot be reduced because I don't have a common variable to all 3 of those terms. I can get rid of the 1 and just say arctangent of 2x. I can cancel out a 4 with those 2 and make that 2. And that'll give me minus 2x over 1 plus 4x squared. And notice, something I didn't see till just now, that I've got a positive 1 and I've got a negative 1. So those 2 cancel, and I'm just left with the arctangent of 2x. Wow, that's pretty cool. And that's going to be my final answer to that particular problem. Okay, last one of the day. Keep hitting the plus, and I don't really want to do that. I'm looking at number 100 on page 380, and there is a little diagram that comes along with it. And that little diagram looks kind of like this. And they basically say this, excuse me, that you have a camera that is sitting 800 feet away from a rocket that's taking off. So you got an H here, and they say that the distance between the camera and the rocket is s units. So we've got this right triangle there. And the, excuse me, I'm just going to read through it. It says a television camera at ground level is filming the liftoff of a space shuttle at a point 800 meters from the launch pad. And I have feet and they want me to have meters. So let's make that change right off the bat before I forget. Let theta be the angle of elevation to the shuttle, and let s be the distance between the camera and the shuttle. See the figure. Write theta as a function of s for the period of time to which the shuttle is moving vertically. Differentiate the result to find d theta over dt in terms of s and ds over dt. Okay, so here is my angle theta. That's my angle of elevation. And if I were to write an equation that is relating s and theta, well, I only have one constant. I have that m. I won't be using AH because I don't want to introduce an additional variable. I've already got two to deal with. So if I look at these three things, well, I've got my hypotenuse, I got my angle, and I have my adjacent side. And so to me, that says cosine right off the bat. So I say that the cosine of theta is equal to 800 over s. Now that's just getting me started because the directions say write theta as a function of s for the period at which the shuttle is moving vertically. So they want theta by itself. So theta as a function of s only is going to be the cosine. Are they actually we'll use their terminology because I want to get cosine by itself. So I'm going to take the inverse cosine of both sides. So I'm going to rewrite it the arc cosine of this 800 over s. So that's the first part. There's my first answer that they want for that. Now, excuse me, the last thing they ask us to do is they want us to find d theta over dt in terms of s and t. So I'm essentially, when they say d theta over d theta over dt, they are talking about the change in angle over, and since they're using t, the change in t, whatever that means, I'm assuming that it's going to be time, but they don't actually ask us to solve anything, so we're okay. And then they say in terms of ds over dt. Well, again, this is the change in distance, so over the change in t. Now again, I'm assuming that that's going to be time, and so this is the instantaneous speed t seconds after liftoff. So I'm going to do the derivative of this, going to derive with respect to t, and this, remember, is an implicit differentiation because I don't have t as a variable here. So I got to assume that it's a differential, or I'm going to have a chain somewhere. So this first one will just be d theta over dt, which is what they want us to find. And then the arc cosine is going to be this. Well, that arc cosine, remember, from way back up here, and is going to be negative u prime over the square root of 1 minus u squared. So I'm going to have, and I'm going to actually, you know what, let's move this down because I know I'm going to run into the next one because I don't want to run into that here. Okay, so I'm going to have the derivative of this expression. So I have to do d over dt of this 800 over s, which I'm going to eventually have to do, over, it was, because it's the arc cosine, and this is negative. Don't forget that. Don't forget your negative. The square root of 1 minus this expression squared. So if I want to put that in there. Yeah, we'll just leave it like that. 800 over s quantity squared. All right, now the derivative of this thing. So I'm doing d over dt, and I'm going to rewrite this because I don't want to do a quotient rule on it. So I'm going to go 800 s to the negative 1. So doing the derivative of that, I've got 800, and then it's going to be, I'm going to multiply by negative 1, s to the negative 2. So this thing, ds over dt, or ru prime, is just going to equal 800, or negative 800 over s squared. So just plugging in everything at the end there, I'm going to have, and I want to just make it usable. So negative, negative, negative here, and then a negative here. It's going to be positive 800 over s squared all over the square root of 1 minus 800 squared over s. Now let's do it right. 800 squared over s squared. And because this is under a radical, there's nothing that I can do to reduce that. And I've got a radical, so making a fraction, that's going to be kind of a pain in the butt. So we're going to accept this as a final answer, knowing that if it was a multiple guess question on the AP Calc test, that you might have to do some manipulation to get it down. All right, kept that right around 20 minutes. That's not too bad. This is the end. Again, if you have any questions, please feel free to leave a comment, and I will try and get back to it. And we will talk about this next week. Have a good day.